The Gaussian elimination method has different variations. This video will show the flow of using the method in upper triangular form. Welcome to Numerical Solutions to CE Problems. In partial pivoting, the only procedure used is through row operations, regardless of the resulting matrices form. In the upper triangular form, zeros are found below the main diagonal. On the other hand, the zeros are located on top of the diagonal in the lower triangular form. Here is an example to show how partial pivoting works. Say we got a system of equations, x plus 3y plus 4z is equal to 4, the second being negative x plus 3y plus 2z is equal to 2, and lastly, 3x plus 9y plus 6z is equal to negative 6, and we are to look for the variables. Again, we convert the system into an augmented matrix. Then we determine the pivot element to be placed in element 1, 1. In such a case, we notice that there is a row with already 1 on the x column. So we might as well take this row as the pivot row and have 1 as the pivot element. Next is to zero out the other elements in the first column. In order to do just that, for element 2, 1, which is just negative 1, we can just add rows 1 and 2 as the new row 2. Then we can start with element 2, 1 having 1 minus 1, which is 0. In element 2, 2, there are 3 and 3 to give 6. Then in element 2, 3, we can compute 4 plus 2 resulting to 6. And for the constant, 4 plus 2 is again 6. Next is to zero out element 3, 1, and that is to equate row 3 with the current row 3 minus 3 times row 1. For element 3, 1, we have 3 minus thrice of 1, and that is 0. With element 3, 2, there is 9 minus 3 times 3, giving 0. At element 3, 3, we have 6 minus 3 of 4, and that's equal to negative 6. Then the constant has negative 6 minus 3 times 4, which results to negative 18. At this point, it is worth noting that not only was element 3, 1 zeroed out, but also with element 3, 2. So this can help shorten the procedure, as all we needed to do now is to reduce the main diagonal elements into ones. So let's just do the reduction starting with element 2, 2, and we can simply divide the second row by 6. That starts with element 2, 1 with 0 divided by 6 giving 0. For element 2, 2, there is 6 divided by 6 and that is 1. Next, with element 2, 3, it is also 6 all over 6 or 1. And it is pretty the same with the constant. To reduce element 3, 3, we divide the third row by negative 6. So with element 3, 1, we have 0 divided by negative 6 to give 0. Element 3, 2 has 0 divided by negative 6 to have 0 once more. Then at element 3, 3, there is negative 6, which we also divide with negative 6, giving 1. And the constant of negative 18 becomes 3 after being divided by negative 6. So the resulting matrix after the reduction reflects an upper triangular form with the main diagonal elements already reduced to 1. From here on, we will be incorporating direct method to solve for the values. Remember that the first column contains the x coefficients, y for the second column and z for the last. If we focus on the last row, we can see 1z is equal to 3. Then, we use back substitution to solve for the other variables. Moving back to row 2, we can interpret the row as y plus z is equal to 1. And z determined as 3, we plug this to the equation to come up with y plus 3 is equal to 1. And by transposition, we have y equal to negative 2. For variable x, we also have another back substitution extracting the first row, which is interpreted as x plus 3y plus 4z is equal to 4. Plug the values we computed earlier to have x plus 3 times negative 2 plus 4 times 3 equated to 4. Simplify the constants to have x minus 6 plus 12 is equal to 4. And with another transposition, we have x is equal to negative 2. And finally, we can summarize the variables as x is equal to negative 2, y is also negative 2, and z is equal to 3.